after the 2-unit parallel configuration, let us look at a slightly more complicated structural system. 1 degree statically indeterminate truss structure, as you see on the screen. So this system has 6 members, and as we know very well, given the sort of boundary conditions it has, this is 1 degree statically indeterminate. So and we can verify this, that if 2 elements fail, then this system becomes unstable. So and we have looked at this problem earlier in a different context, where we looked at cut sets. So this system has 15 different cut sets, each of which has 2 members. It has 15 different minimal cut sets, and each of those minimal cut sets has 2 members. Now let's define the problem in the context of random variables and material behavior. So we have one load H, and there are 6 members. Each of them has a strength which is the random variable, and we are looking at 2 extreme cases. One is that the member failure is brittle, so each member has a brittle behavior, and the other one is each member is perfectly ductile. And in all cases, we are going to take the 6 random variables of strength and 1 for the load. All 7 of them are mutually independent. Now, in a situation such as this, we would need to identify the minimal cut sets, at least the probabilistically dominant ones, and then find out if we need to consider any sequence effect or not. That depends on our understanding of the mechanics of the problem and how the intact structure finally goes to global failure. And then we need to find the probability of each such cut set or sequence within the cut set, and then obtain the union failure probability. For this simple structure, we have been able to identify all the 15 minimal cut sets, but it doesn't have to be so for a larger, more complicated structures. But let's continue with this, and let's look at case 1 first, where the members are all brittle. So here let's define the terms properly. So D0I, 0 in the superscript, I in the subscript, it means it stands for the force in member I, and that 0 in the superscript means that none of the members has failed. So it's the intact state of the structure. Dij, or I in the subscript, J in the superscript, Dji is the force in member I when member J has failed. Since we have a structure with 1 degree of indeterminacy, so just one number in the superscript is enough for this problem, but in a more general case we would have more numbers in the superscript, and I and j go from 1 through 6. So after having defined these terms, let us now look at the entire situation. So we have 6 members, and their lengths and areas are all specified. So let's look at this table column by column. So the column which is D0I, so the force in the structure in all the elements when no member has failed, so that's the intact state, 0 state, and there we have the 6 member forces. Negative implies compression, but our assumption is that the strength in compression and tension have the same absolute magnitude. So that is the intact state, and now let us look at the next column. So when element 1 has failed, and because it's brittle we have just removed it, so that's D superscript 1, and then with that damage we look at the forces in the remaining members. So now we effectively have a determinate structure. It's quite simple to solve. For member 1 itself, obviously it doesn't have any force because it has been removed. For all the other 5, we have 3 that are loaded and 2 that are not loaded. So that's actually going to be useful later on when we try to look at which sequences are going to have what sort of contribution to system failure. And likewise, we can get D2, I, D3I, D4I, D5I, and D6I. And you see all the diagonal terms have NA because the member has been removed for that particular column. And some of these are not loaded at all. In each case, we have 2 elements that are not loaded at all in each case of one member failure. And we'll come back to this, but it's interesting to note that there is some sort of symmetry in the loading in between different columns, which again will be useful for us when we compute system failure probability. In the next slide, let us define failure sequences. So let's first start with FJI. So J in the superscript and I in the subscript, and that stands for, consistent with what we did in the 2-member parallel system case, failure of only member I when member J has failed. And let's also write Ci for capacity of member I, and let's make the reasonable assumption that the capacity of a member does not change with damage state. So even if other members have failed, the capacity of any surviving member is the same as it was when the structure was intact. Now with these 2 things defined, let us define F01, for example. So that means that from the intact state, member 1 fails first, only member 1 has failed. So that would happen if C1 is less than D01. So member 1 is not able to carry the load in intact state, but all the other members are able to carry the loads given on them in the intact state. So that is intersected with C2 greater than D02, C3 greater than D03, all the way up to C6 greater than D06. This then we can take to the next step, that let us say member 2 fails second. So F01-2 would be the same events that were also that are there in F01. So C1 less than D01 will be there. D02 D02 is less than C2 as we had before, but then C2 is no longer able to take the load after member 1 has failed, so C2 is less than D12. So we have one combined event, that C2 is greater than D02 but less than D12. For all the other members, they continue to survive the second level loads as well. So C3 is greater than both D03 and D13. So that's why we have the max operator. C4 is greater than max D04 and D14, all the way up to C6 greater than max D06, D16. So you're getting the idea that things become quite complicated quite soon when we have this sort of redundant system failure to be modeled. And now putting the values from the previous slide where we had that table of all the loads, we can write F01-2 and F01-3 for all of those different sequences in terms of the C's and H. H is the applied load, and we already know what the member forces are under various intact or damaged conditions. Also, we could write the simultaneous event F0, 1 and 2, which is both 1 and 2 fail in intact state and the others don't. So C1 less than H over 2, C2 less than H over 2, but all the other ones are greater, C3 greater than H over 2, and so on, C6 greater than H over root of 2. So this way we can define all the necessary sequences. If we know which sequences are dominant and which sequences can be neglected, we don't need to do all of them. We can only look at a few important ones. But here again we are looking at the entire enumerated set. So this is to summarize all these things putting together. So this is the load table, and we can see from the symmetry of the problem that F01-2 and F02-1 will have the same probability, and you see all the other pairs that also have the same probability, and that's because the capacities are independent, identically distributed, and the loads are as they are in the above table. So this is obviously not a general situation. It depends on some of the simplifying assumptions that we have made for this problem. And likewise, we can see that F01 and 2, F01 and 3, etc., they also have the same probability. Now, we can see by inspection that's because if you see in the load table in the column D1I, member 4 and member 5 have no loads, so they just cannot fail. So if member 1 fails first, then 4 and 5 have no possibility of failure. So that sequence 1-4 and 1-5 obviously is not going to happen. So that's why we see some of those easily identified zero probability sequences, P of F01-4, F04-1, all of those have zero probabilities, and it's good to know them because we won't have to worry about them, we don't have to compute them, we don't have to simulate them. But this is the description of the entire system failure event. It's the union of all the sequences and the union of all the simultaneous failure events, and it so happens the way we have defined this, they are all disjoint because if it's 0 and then 1 then j, or I then j, then obviously it is going to be disjoint from all other sequences in another event when another member fails first and some other member fails second. So clearly the way we have defined this, these sequences all are by definition necessarily disjoint. So it's helpful because we can add the individual probabilities to get the system failure probability. There's a p missing after both the sigma signs. So it's p on the right hand side, it's p f0 I dash j and p f0 I and j. And there are 30 such sequences that we need to consider to be complete, and 15 such simultaneous failures that need to be considered. But again, as we saw, quite a few of them are impossible events. So putting now after the computation, we can tabulate all of them, and let's look at a few of those. So let's look at the very first set of rows. So it's the member sequence 1 then 2 and 2 then 1, and on the right you have 1 and 2. So 1-2 and 2-1, they have the same failure probability. The failure probability of the 1 and 2 event, it's almost an order lower. So in many cases, we can actually ignore the 1 and 2 type of simultaneous failure events. Let's look at the next one, 1-3 and 3-1. That was a mistake. It shouldn't have happened. The system failure probability was supposed to come out last, but we'll look at this at the end. So we have 1-3 and 3-1. You see that they are also the same, whereas 1 and 3 is about an order smaller. 1-4, 4-1 and 1 and 4, it's interesting. Even though the sequences will never happen, the simultaneous events do happen. The same goes for 1-5 and 5-1. And in fact, 1 and 5 is one of the more likely events. So we will not be able to ignore that. Here we see for the first time an unsymmetrical situation. So 1 then 6 and 6 then 1 do not have the same probabilities. So that's why if we have a cut set, we need to find out which ordering of those members in that minimal cut set need to be looked at, and others may be ignored. And that's here, this minimal cut set of 1 and 6, they do not have the same probability in different orders. So 1-6, 6-1, and 1 and 6, they're all different. And this way, we can compute all of them and sum them. So it's 5.6 10 to the minus 3 for the sequences, 1.1 10 to the minus 4 for the simultaneous events, and if you add them, the system failure probability is about 5.7 10 to the minus 3. We need to remember that, because the next case we are going to look at is the it's the ductile system, and we'll see how the answers change. So we come to example I2B, our 6-member indeterminate truss with ductile member behavior. So all the properties are the same as case I2A, when the members were brittle in nature, but because of the ductile nature, this load table is going to look substantially different. So let's again recall the definition. D0I is the force in member I when the truss is intact. DJI is the force in member I when member J has failed. So the first column is for the intact structure, and it's the same that we had in the brittle situation also. But now, as members start to fail, so we have D1I, D2I as in the brittle case, we see that it's beginning to look different, because now if member 1 has failed, it still carries the failure load because it's now fully plastic. So C1 is the load present in member 1 effectively, and so that C1 shows up in all the other member forces, and that's what you continue to see when looking at all the other columns. So D2I, D3I, D4I, D5I, and D6I. So all the member failure events now would look a little more complicated. So let's take a look at that. Let's define, as we did before, FJI is failure of only member I when member J has failed, and CI is the capacity of member I as before, and DJI is what we just defined. So F01, the event describing that member 1 fails first, when the truss is intact. So again, as we did in the brittle case, C1 is less than D01 and C2 is greater than D02 all the way up to C6 greater than D06, because we are only interested in member 1 failing and the others not failing. And then we do F01-2. So that is again looking at C1 has failed and C2 is between D02 and D12, and all the other capacities are greater than the loads put on them at both stages. So that way we can now bring in the actual load values from the load table in the previous slide, and we can define the event F01-2, where again you see all the max functions because we have that in place already, and you see all the CIs there in the max also. So when one has failed, it does not mean that C1 has vanished. So C1 actually shows up in these limit states repeatedly. So we can do this for all the 30 failure sequences and 15 simultaneous failure events that we described in the previous slide, and as we did in the case of the brittle failure, we can look at each minimal cut set wise. So 1, 2, then we have 1, 3. That system failure probability was supposed to come out at last, and then 1, 4, and so on. The interesting thing to note is that because of the perfectly plastic behavior, because of perfectly ductile behavior, all the sequences, whether it's 1-2 or 2-1, they have the same probability. And if we just looked at the cut set, we would simply be adding 1-2, 2-1, and 1 and 2 to get that minimal cut set probability. So we go through all of them and we sum them. We get 5.8 for 5.8 10 to the minus 4 for the sequential events, 1 times 10 to the minus 4 for the simultaneous events, and the sum is about 7 in 10 to the minus 4. Compare this with about 5.7 10 to the minus 3 in the brittle case. So just by replacing the brittle elements with ductile elements, the failure probability goes down by a whole order of magnitude.